Welcome back to our session. We're still looking at internal resistance, but now we want to take a turn and actually look at an investigation that we can practically use to determine internal resistance of a battery. But think about it in terms of the scientific skills. So we shall try and manipulate variables, within the context of a circuit. And at the end of it all, we want to use our findings to actually determine or calculate the magnitude of internal resistance of a battery. Let's have a look at it now. Right. The big question which we want to focus our attention on now is around the fact that we are saying, is the internal resistance of a battery? So internal resistance is always the resistance inside the battery. So the question says, is the internal resistance of a battery constant when current passing through the battery changes? Right. This is an investigative question of some sort. Now we are asking ourselves that if we change the amount of current that passes through the battery, or that passes through the resistor inside the battery, is the resistance of a battery going to remain constant? So we can also rephrase the same question and ask ourselves, okay, does the internal resistance of the battery change depending on the current that passes through it? Or is there any correlation between the amount of current passing through the battery and the magnitude of the battery's internal resistance? So we can ask the same question in different ways, but the key thing is that we're going to vary the current or change the amount of current for the same battery to see if that in any way does it affect the magnitude of internal resistance. So that's the big question, right? Okay. Now we are saying that we are going to measure the terminal voltage, okay? This is across the battery, very, very important. We're going to measure the terminal voltage for the different current readings, right? So we're going to connect a voltmeter across the ends of a source and for different amount of current that passes through the battery. So if we vary current, okay, it means current is the independent variable. Okay, this is very, very important. What's an independent variable? Is that physical quantity that we manipulate in our attempt to discover or verify a scientific fact. Okay, so in this experiment, we're going to change the amount of current. How? We shall establish, right? So current becomes our independent variable. Now in response, so this is our response variable, right? In response to changing current, this is, we're going to measure the terminal voltage, which is our V external. Think of it. This is still across the battery, but it's only in a closed circuit, right? So remember, right, we have said the same question in many ways. We are saying, is there a theoretical relationship between current and the terminal potential difference, right? While we measure terminal voltage for a closed circuit, okay, for the same battery, we also want to establish whether there is a theoretical relationship between current and terminal potential difference, right? Okay, but bear in mind the equation E, which suggests that EMF, which is the maximum energy per coulomb of charge that can be dissipated by the battery, is equals to, this is our internal or lost volts, and then that's our external voltage, which is V terminal. So this is our V external, in other words. Take note of the notation, and then that is our V internal, okay? So the maximum energy, which is dissipated by the battery per coulomb of charge, is actually split between internal and external voltage or potential difference, right? So there will be variations of representing the same formula, in different ways to say E is equals to V internal, which is the lost volt, plus V external. We're still saying the same thing, right? Okay, so we are going to look at that equation and try to express it in terms of the equation of a straight line. So that's some mathematical skills that are very important that we need to bring to the fore, right? So if we make V external the subject, we appreciate that it will give us negative V. So in other words, V external, okay, is equals to V internal, negative V internal, okay, right, plus EMF. Okay, so this is the same as EMF minus V internal gives us V external. Okay, so if we apply the Ohm's law, we know that from the Ohm's law V is equals to IR. Okay, but also V internal is equals to I small letter r. Okay, we're still applying the Ohm's law. It takes us to that. So if we remember very well, M represents the gradient, right, of a linear graph, okay, which is always constant, and C is the intercept. Okay, so the intercept is E in the sense that if this is 0, the V external or V load equals to the EMF. So when there is no current in the circuit, the intercept of the graph, or the maximum value when there is no current, will equal V external, and that maximum is actually the EMF. And then the gradient is M is equals to -1. It means this linear graph actually has a negative gradient. Right, so let's go back to our practical now and do the investigation, so that we are able to determine the internal resistance of a battery when we change current, okay, and then we measure the terminal voltage across the battery. Right, okay, so what is it that we need to set up this simple circuit so that we can determine internal resistance of a battery, which is our small letter r? Okay, what do we need? In this case, we'll use a 6-volt battery. It can be any battery for that matter, okay? This is not prescriptive. So as long as there is a battery with some voltage, I think it's proper that we can safely say that you can be able to determine its internal resistance. An ammeter that will measure our current through the battery or through the circuit. A voltmeter that will measure the voltage. This one is going to be connected across the end of the battery because we are interested in measuring V external. And then this should give us the total current, the connecting wires, and a variable resistor. Right, there's something very interesting about the variable resistor. We are going to use this variable resistor to actually change the magnitude of resistance, which will affect the current. And then as a result of that, we'll measure the terminal potential difference. Right, so this is how the circuit looks like. Okay, so that's our variable resistor there, right? Okay, so the voltmeter is measuring V external in this case if the switch is closed. So this is going to measure the total current, right? So bear in mind the amount of current that passes through the ammeter is equals to the current that passes through the internal resistor of the battery. So if we use a simulation, it will definitely look like this. Right, so when the switch is open, okay, this is an open circuit, right? So this potential difference across the battery is actually giving us the value of the maximum reading, which is the EMF, when there is 0 current in the circuit, right? So we're going to vary the resistance of the resistor and then measure the terminal potential difference while the switch is closed, right? So we'll set up the resistor to a high resistance and then adjust it accordingly and correspondingly take the values of terminal potential difference. So take the voltmeter and the ammeter readings while the switch is open. This is the starting point, okay? Then we'll close the switch, vary the resistance, and take our readings. So as we continue to decrease the resistance of the resistor while the recording of current and voltage across the battery goes on, we'll be able to obtain a set of values of this nature. So this was while the switch was open. Okay, take note of that because it has a lot of implication in terms of the interpretation of this data that we have obtained. And also pay careful attention to the trend. Right, the value of current is forever increasing. Remember, as you go from open switch and we close the switch, while we adjust the resistance, the amount of current got higher and higher. Pay attention again to the value of V external. So these are values of what? V external, in other words. Okay, so this is the graph that we'll obtain. Okay, so we've got current as the independent variable and voltage as our response variable. Pay attention to the graph there, right? Okay, now if we are to identify the variables, remember we said the dependent variable is terminal potential difference, or terminal voltage, right? So this is our dependent variable. We manipulated the current, okay, which is our I, okay? And then this we said is our V external, okay? And then the control variable in this case, we try to keep the temperature constant, because how we carry out this investigation is also very important. So we need not connect it for a very long time, and we need to keep the temperature constant because there are some implications in as far as the Ohm's law is concerned. Okay, the first question says, is the gradient of the graph constant? It is definitely constant, yes, because this is a linear graph, okay? There is a linear graph, okay? And we said that the gradient of this graph actually represents the negative value of actually the internal resistance. All right, okay? And then if the graph, is the graph positive or negative? The graph is definitely negative, okay? The reason for that is that if you go back to this graph, you'd realize that as we decreased the resistance, the current increased while V external was decreasing, right? So there's a very important relationship between V external and current, okay? Why? Because as current, we are saying current increased, okay? We increase current by decreasing the voltage, the resistance. So in other words, we are saying resistance, external resistance decreases, right? So external resistance decreases, current increases. Now, once that happens, it means V external will also decrease. So these are the theoretical relationship that exist. Okay, very, very important. Right. Use your graph to calculate the internal resistance of the battery. So the theoretical, so we are looking for this negative gradient. That's our internal resistance. Okay. That's our internal resistance. Okay. So if we are to use the graph to do that, we can take any set of values. So we are saying this negative gradient R represents its absolute value actually. So we can take any two coordinates there. The first coordinate, we can use the 6, 0, the 0, 6, okay, which is the intercept, and also we can use that. That value is, if we are to apply our change in y over change in x, in this case is going to be 2, and then that goes with 4, right? So our change in y is going to be what? 6 minus 4, okay? 6 minus 4 over 0 minus 2, right? So this gives us what? 2 divided by negative 2, this gives us negative 1. So the absolute value of this negative gradient actually gives us the internal resistance. So the internal resistance of this battery is actually equals to 1 ohm, right? So that's the very important part, okay? So the EMF of the graph, we're saying it's the maximum. When there is zero current, V external is equals to the EMF. So our value of EMF is actually equals to 6 volts. Right. Okay. So the big question that we ask is that, is the internal resistance of the battery constant when current passing through the battery changes? We can conclude that, yes, indeed, the internal resistance of the battery remains constant when the current passing through the battery is changing, because this resistor inside the battery is actually an ohmic resistor. That's why it definitely obeys Ohm's law. Right, we'll take a short break for now. When we come back, we'll look at more of interpretations on questions that involve internal resistance. See you after the break.